Good afternoon, everyone. Welcome to our colloquium talk for this week. I'd like to introduce Associate Professor Milena Radnovic from the University of Sydney. Milena's research interests are in integrable dynamical systems and mathematical billiards. And she's a member of the Integral Systems group at the University of Sydney. Last year, Milena was awarded an ARC Discovery Project for billiards within confocal quadrics and beyond. And today she's going to be talking about Ponsoliporisms and billiards. So with that, I'll hand over to you, Milena. Thank you.
First, I would like to thank David and Macquarie University, the School of Mathematics, for inviting me to present, to make a talk at this colloquium. So I will start right now. Okay, so I hope that you see now my presentation on screen. So my talk will be about Ponsoliporisms and billiards. So this is a topic that I've been interested for many years. And I will like today to present to make some historical introduction into that topic, but I will at the end also try to present some new results concerning Ponsoliporisms and billiards. So let me first explain about Ponsoliporism. Consider the plane. We can imagine Euclidean plane or projective plane, and that we have where we have given two conics or two second order curves in that plane. And now imagine that we play the following game. So we start from one point on one of those conics, and we draw a tangent a line to the other conic here. So this is the red tangent line. That line will intersect the initial conic into another point, since line and the conic always have two intersection points. Okay, then from the second point, okay, so this is the second point in the drawing. We now draw from the second tangent line to this inner conic. So again, as every line intersects each conic in 2 points, also from any general points in the plane, we will have two tangent line to a given conic. So here, after this step becomes unique. We get from the first segment, we get the second segment is uniquely determined. Then we get the third intersection point on the outer conic. So we continue, we draw the third segment, which is now uniquely determined, the fourth segment, the fifth segment, and the sixth segment. And here, after the seventh segment, we got we came back into the initial point. So we got a closed polygonal line here in this case. So this is a very special case. One can imagine that such things that we were in this drawing very lucky to get a closed polygon here. And that in generally, if we try that to play that game of inscribing a polygonal line in one conic and circumscribing it about the other one, that generally such a polygonal line will never become closed. So this is just a very special case. But now let's try another one. Let's try the same, knowing that we have a closed heptagon inscribed in one conic and circumscribed another one. Try to do the same, to play the same game but now starting from another point of the outer conic. So this is the first segment here. So there we have the second blue segment, the third one, the fourth one, the fifth one, the sixth one, and finally the seventh one again becomes closed. So this is an interesting coincidence in this case. And in fact, this is the statement of the Ponsoliporism. Now I will give here the formulation of the Ponsoliporism. So it says as the following, as follows. If there is a closed polygonal line inscribed in one conic and circumscribed about another one in the plane, then there are infinitely many such polygons, and all of them have equal number of sides. So this is in fact a special case of the great Poncelet theorem, and I will tell later in this lecture a bit about this more general statement, which is the great Poncelet theorem. I will tell a few words about that later. But now I would like to tell a little bit more about this statement. This simpler statement that I formulated here is nowadays known as Ponsoliporism. So I would like to tell two things. One thing I would like to tell about the word porism, and the other I would like to tell a little bit about the history of this statement. So porism is a word from Greek, and this is this was used by ancient Greek mathematicians. So generally they were classifying mathematical problems into two categories. So one category were theorems, and the other category were constructions. So in theorems, generally, some property of mathematical object is claimed, while in construction it is asked to construct some objects with certain properties. Porisms were mathematical kind of problems or statements which were by their classification neither theorems nor constructions. So why this Ponsoliporism deserves that porism name? So you can imagine the following construction problem. We say, okay, let's have two conics in the plane. Please construct a heptagon inscribed in one and circumscribed about the other one. So that sounds as a completely legitimate geometrical construction problem. However, we see here that such a problem either doesn't have any solutions, which in fact will happen in the most cases when you have two conics, or if they're in such a special case, then the solution of that construction problem is trivial, and we have infinitely many solutions, and it is trivial to get them. So you can start simply construction from any point and just draw continue drawing the polygon, and you will get a solution. So this is something that the Greeks would call a porism. Okay. So now I would like to tell a little bit about history of the Poncelet theorem. So the Ponsoliporism or Poncelet theorem. So as you can see here, the year when Poncelet got it was the year 1813, very beginning of the 19th century, and The year was the year, just as we can recall from our history lessons, just was the year after the Napoleon's attempt to invade Russia. So the Poncelet was in that year very young. He was only 24 years old, and he just graduated before that from École Polytechnique, and was mobilized as a junior officer to Napoleon's army, and so joined that war to the east. So for Poncelet, that finished in the famous Battle of Krasnoy. So here is artist view of that battle, where French army was heavily defeated by the Russians, and they withdrew very quickly from there, leaving their dead and wounded soldiers on the field. And Poncelet was was wounded in that battle. His horse was killed under him, and he was just left there. Next morning, after the battle, him together with the other surviving French soldiers were picked up by the Russians. And so Poncelet spent the next 2 years in a military prison, mostly in Saratov. And that was in Saratov where Poncelet was in his famous notebooks from Saratov, was recalling his geometry lessons from his own education. And not only that he recalled them, but he got this great Poncelet theorem, which after turned out to be one of the most important and most deep geometrical statements from the 19th century. So these were the conditions in which the theorem was proved, and also just to mention that Poncelet was very young, so he was not a scientist and he was not a mathematician, which I think just tells about the greatness of Poncelet himself. Okay, so I just want now to mention some of the about the interest that Ponsoliporism drew in by some famous mathematicians. So it was Jacobi who proved that the Poncelet theorem is essentially equivalent to the addition theorem for elliptic function. Then we can find a very beautiful proof from the beginning of the 20th century by Lebesgue in his textbook on conics, and he gave a proof in an elementary very beautiful way. And also it's worth to mention that Griffiths and Harris as a leading algebraic geometers of modern times were also interested in that, and they gave a modernized version of Jacobi's proof of the Poncelet theorem. So the Ponsoliporism is the interest in Ponsoliporism revived at the beginning of somewhere towards the end of 20th century, and there is a whole body of new results regarding Ponsoliporism. Okay, now I want to explain how is Poncelet theorem, Ponsoliporism related to mathematical billiards. So let's first define a mathematical billiard. So the mathematical billiard is a dynamical system where we have a particle which freely moves without friction within a certain domain. And it reflects absolutely elastically off the boundary. What it means that it will reflect absolutely elastically according to the billiard law. So that means that the speed of the particle will not be lost, so no energy is lost in bouncing in the reflection. And we will have the impact and the reflection angle to be equal to each other. So the trajectory of a mathematical billiard will be a polygonal line who's inscribed in that boundary of billiard. So mathematical billiards are a very popular topic in today's mathematics, and there are they can be studied from various aspects, but very popular are, for example, polygonal billiards. But I will today I will tell more about elliptical billiards, which are integrable. Okay, so in elliptical billiard, we have a boundary which is a second order curve or an ellipse, because we want it to be, the billiard domain to be compact. And there is a famous focal property of elliptical billiard, so which says that if a billiard ball passes through a focus, then after bouncing off the boundary, it will pass through the other focus. So in this illustration here, we have these two billiard balls placed in the foci of that ellipse. And then that means that if you hit one of them in any direction, after bouncing off the boundary, it will necessarily go through, hit the other ball. Okay, next we can ask what is happening with the trajectories of elliptical billiards if they do not go through any of the foci. What is their behavior? And now they have again a nice geometrical property. Such trajectories always have so-called caustics. So that means that there are curves which are touching each segment of such trajectories. So here in illustration we have two various examples. So if a billiard ball doesn't go through the foci, it can you can have two cases. It can either go between the foci, and then after bouncing off the boundary, it will again pass between the foci, and moreover, it will touch one hyperbola, which is confocal with the boundary. So it has a common foci with this elliptic boundary. On the other hand, if the billiard particle doesn't go between the foci, then again it will after bouncing that reflection, that property will be still true, and there will be a confocal ellipse touching both segments of that trajectory. And of course, now that will continue further and further. So all further segments will be touching the same curve. And so such curves are called caustics. And in fact, the caustic here, these caustics represent the geometric manifestation of integrals of motion. So each billiard in a plane has one integral, which is, one trivial integral. This is the energy integral. But the other one, the existence of the other one is, for elliptic case, is guaranteed by this existence of caustics. Okay, And now let us see so the trajectories of elliptical billiards are inscribed in one second order curve and always circumscribed about the other one, which is a caustic. So we see that we can directly apply the Ponsoliporism. And now here it is a Ponsoliporism formulated in this billiard, in the billiard language. So we say, if there is a periodic trajectory of elliptic billiard, then all trajectories sharing the same caustics, the same caustic will also be periodic, and in fact will be periodic with the same period. And here we see, for example, a family of triangular billiard trajectories sharing the same caustic. Okay. And now, after this billiard formulation, I would like to tell about the great Poncelet theorem. So this is the generalization of this, what is nowadays usually called Ponsoliporism or Poncelet theorem. And Poncelet, in fact, proved this the more generalized statement. And this statement in the billiard formulation says as the following. Now we consider the billiard game, but now it is not anymore billiard only with one boundary, but we consider a family of several ellipses which are all confocal. So it is essential here that they would be all confocal. So we have here 3 different ellipses as there, and we play the following billiard game, which we prescribe in advance how to play. So, for example, in this case, we have the following recipe. We say you bounce 3 times off the middle of these 3 ellipses, but from within that ellipse. We bounce once from the smallest of the ellipses, but from its outside, and we bounce once off the most outer one ellipse. And then in this case, as you see the illustration, this trajectory is closed. So, and then the great Poncelet theorem says, if we get a closed billiard trajectory with this of such a now more complicated billiard game, then the trajectories will be closed independently on the starting point of our game. So just here, I will show the illustration for that. Just here, I would like to emphasize that the trajectories of such a billiard game will still have this caustic property. And they have it because these the boundaries are all confocal. So there will be a curve, second order curve, confocal with them, which is touching all segments of the trajectories. In this case, when we have bouncing from outside, although this segment itself doesn't have common points with the caustic, but its extension will have. So the extension will be tangent to the caustics, and similarly the extension of this segment. Okay, so the caustic property is still preserved, and this is essential here for consideration. And now we see another trajectory here. The blue one is again a trajectory constructed by the same rule, but starting with other initial conditions, but having the same caustic. And we get again the closed billiard trajectories. But moreover, there is one more kind, not only that we can choose a point from which we can start, but we can do even more. We can interchange the order of our moves. So if we said here we bounce 3 times off the middle ellipse, once from outside from the smallest ellipse and once more from the biggest ellipse, the order of these moves is not not important. So we can interchange. We can, as here is depicted, go bounce once and then the second time off the middle ellipse. Then we bounce off the outside of the small one. Then we bounce off again of the second ellipse, and then off the third, and again we get the closed trajectory. So the essence of this, that we can interchange the order, is in fact this configuration, which can be seen here, and which is called double reflection configuration. So that means that you have two consecutive reflections of two conics. You can interchange their order, and from initial segment, go in one order or in the other order, but you will go the outgoing segment will be the same as the same with both ways. Okay, and this is the great Poncelet theorem. This is the great Poncelet theorem, which was obtained by Poncelet. Okay. Now, I would like to tell about one consequence of the Poncelet theorem, which was proved by Darboux, and where he was considering those polygons obtained by those constructions of Poncelet. So here is the extract from the original of his great lectures on surfaces from the end of 19th century. And up to my knowledge, in fact, it was in Darboux was the first one to consider to see this billiard connection of with the Poncelet theorem, and he was the first one to consider higher dimensional generalizations of Poncelet theorem. Which were these results of Darboux, in fact, were fairly forgotten by modern mathematicians until we found them some maybe 15 to 20 years ago. Yeah, okay, so here what is Darboux claims in this theorem. So he claims as follows. Now we consider again a trajectory of a billiard game. Now this is a bit more complicated billiard game. So it is not only one boundary, but we have several boundaries. In this case, on this illustration, we have two boundaries, and we have the rule that we bounce once, twice, 3 times, 4 times, 5, 6. So 6 times of the inner ellipse and once of the outer one. And in this case, with this caustic here, we got a closed trajectory. By the great Poncelet theorem, any other starting from any other point following the same rule, we will get again a closed billiard trajectory. But Darboux theorem says more than that. It says the following. Now consider the following. This kind of polygon which we get generally will have the sides will have a self-intersection, will intersect each other at inner points, not only the two consecutive sides have a joint vertex, like for example here. And let's consider the following. So consider, for example, this would be the first side of the blue polygon. Then we have the second, the third, and the fourth side. Okay, so this point is the intersection of the first and of the fourth side of this blue polygon. Then the next point is the intersection of the second and of the fifth side of the same polygon. This one is the intersection of the third and of the sixth side of the polygon. And Darboux's theorem, we have this point here as well. The Darboux's theorem says that all of those points will belong to one conic, which is confocal with the boundaries. And in fact, this curve remains unchanged for any Poncelet polygon corresponding to this configuration. As we can see here for the illustration, that the corresponding intersection for the green polygon also belong to this red confocal ellipse. Okay, so Darboux formulated this in a bit more general setting. He considered, in fact, confocal families of curves on general Liouville surfaces and proved this statement for any closed polygon there. So the one generalization of that theorem was we got jointly with my collaborator Vladimir Dragovic some more than 10 years ago, where we consider in the Euclidean case, but we have shown that such property will be satisfied also by any kind of billiard trajectories and not only closed ones. So, and here in this illustration is these are those corresponding intersection points are denoted by green here. They are in fact, these figures are obtained by computer simulation. And we see nicely that here, for example, those ones are sitting on the branches of a hyperbola, or those ones on a confocal ellipse. Okay. Okay, but now let's go back to just a simple billiard within an ellipse. So without that complicated billiard games where we have multiple boundaries. And if we look closer into periodic trajectories, we can easily see that we have different types of those periodic trajectories. So for example, we have here on this figure, you can see 3 trajectories, which are all periodic with the same period. They all have, they are all 7 periodic, but they are geometrically different. What is difference between them? So the difference between them is that the first one will, along its period, make only one round, around the center of the ellipse. The second one is winding twice around the center before becoming closed. And the third one is winding 3 times around the center before becoming closed. And each of such of those types of trajectories have their own caustic, as we see here. So we can introduce the rotation number as a more precise way to characterize periodic trajectories, since we see that the period is not enough, as the following fraction is the number of windings about the origin divided by the number of reflections. And in fact, the rotation number also has a sense for non-periodic trajectories, because we can along non-periodic trajectories, along some initial finite part of non-periodic trajectories, we can calculate the number of windings made up in that initial part, divided by the number of reflections, and the limit as the length of trajectory goes to the infinity will be the rotation number. That rotation number is irrational for non-periodic trajectories, while for periodic trajectories is always a rational number. And it's in fact nice to see, because the denominator is always the period, while the numerator is the number of windings along the trajectory. And now we can also see that it is pretty obvious and also elementary to prove that the rotation number will change monotonously from 0 to 1/2 as the caustic shrinks. So we see here that if caustic is very close to the boundary, that those segments of trajectories will be closed. So we will have to do kind of a lot of reflections in order to make a round around the center. And as the caustic becomes smaller, that number of reflection is also becomes smaller. We make bigger steps around the center in billiard. So this is a pretty, I mean, obvious almost from the picture. I would say that property. And now let's ask what is happening. We can ask what about the other trajectories, those where we have hyperbola as a caustics. So their rotation number is defined as in a different way. It is more natural to define the rotation number as because as in the number of periods between the branches divided by the number of reflections. So again, we divide by the number of reflections. What is the number of periods between the branches? So each billiard particle will go here always will go somehow in between, and it is we count the number, we count along the trajectory the number of time that this trajectory, the particle went left and right between these two branches of the caustic. And now one can also ask about the monotonicity of rotation number. And so if you make a computer numerical simulation, and by computer one can make graphs and see that this rotation number will also change, seems to change monotonously between as this confocal hyperbola changes. But it is somehow, first, this property is not at all obvious here from picture. It is not obvious that it will change this confocal hyperbola, that how this rotation number will change. And the second, it turns out that it seems it is not possible to prove it elementary. So the only proof of monotonicity, up to my knowledge, of the only proof of the monotonicity of the rotation number was given by Johannes Duistermatt in his book on discrete integrable system from 2010. And it is a very, very non-trivial proof using the theory of algebraic surfaces. Yeah, very non-trivial and hard to read, the proof which is hard to read. So I would like here to say that in fact it was last year that I got together with Dragovic another proof of that monotonicity of rotation number, which is in our opinion, a more simple, a bit more elementary, and moreover allows possibility to extension and application to the frequency function for higher dimensional integrable billiards, which was, by the way, that was the a well-known open problem in the theory of integrable billiards. And to get that, we established a connection with generalized theory of Chebyshev extremal polynomials. And here are references, corresponding references of our recent work regarding that topic. Okay. So I would like now again to go back to history and to see how this Poncelet theory and the Chebyshev polynomials fit together. The Chebyshev with his St. Petersburg school established the modern algebraic approximation theory in the second half of the 19th century. And his motivation was practical ones. It was to estimate the error of the mechanism which transform linear motion into circular. And here there is an illustration for one such mechanism there. And in fact, Chebyshev started that it was the starting point and inspiration for this investigation of Chebyshev was the work on theory of mechanisms of again, Jean-Victor Poncelet, which was known to Chebyshev as the French military engineer, professor of mechanics, and academician. And Poncelet came to the question of approximation of such, expressions of such form, and gave two approaches to that problem. And Chebyshev learned in the mid-19th century in his trip abroad about that work of Poncelet, although they did not, apparently they did not meet in person. And just that Chebyshev described Poncelet as, in his own notes, as a well-known scientist in practical mechanics. So, this is this work is also originated from work of Poncelet, and there we have two streams which were completely independent and not seemingly connected to each other. One is work in geometry, and Poncelet, which originated from the Ponsoliporism, and another one in this approximation theory. And in our recent work, these two streams came together and got to play together. Okay, so so the billiard in higher dimensional space is defined similarly as in the plane one. We have a particle within a given domain which moves freely within the domain and reflects according to the billiard reflection law of the boundary. So in for the billiards within ellipsoids, we will have confocal families of quadrics have the crucial role. And there we have differential equations of lines which are touching the d minus 1 quadrics from a given confocal family. And I know that my time is getting over, so I just want to state a little bit about results, and I will finish my talk. So for analysis, it is, maybe I will skip this, just I want to tell a little bit how these, maybe I will just finish by showing the nice, we proved this monotonicity of the corresponding widening numbers in higher dimensional case using the generalization of the theory of Chebyshev polynomials by Crane, Levin, and Noodleman from the end of 20th century. And just for the end, to show one periodic trajectory within an ellipsoid. So when you have a three-dimensional case, it's not easy to draw on paper a picture which will be easily understandable. So here we have such trajectories have two caustics, but they can coincide if they are both hyperboloids of one sheet. where then the trajectories will be placed along the generatrices of such hyperboloid. And now, using our results, we are able to explicitly construct and prove existence of, for example, 4 periodic trajectories within ellipsoid. So here, only caustic and trajectories are shown. So this is all, and I will finish my lecture here.
Thank you very much. Very interesting talk. Now, I wonder if anyone would like to ask any questions. If anyone would like to ask a question, you can unmute your microphones and jump in.
Could you put up the slide with the Pell's equation again?
Yeah, I will. Yeah, I think that it should be seen now.
Yeah.
So the explicit condition for periodicity of trajectories, in fact, can be written in the other way as a Pell's equation, and we see that the periodic trajectories, existence of a periodic trajectories with given caustic, will be equivalent to the existence of solutions of polynomial solutions of such equation, and then. From there, we get from Pell's equations lead us to this theory of extremal polynomials, since the extremal polynomials on a family of segments will exactly give us the solutions of the Pell equations. So this is the connection.
Thank you.
Okay, would anyone else like to ask a question?
Can I ask a question?
Yeah, sure.
How easy it's to check that this equation has solution, or how it's checkable? What you just mentioned that the periodic solution exists if this equation on your last slide has a solution.
You mean, yeah, well, one can, to check if periodic trajectory exists, one can write that there are generalized Cayley conditions for periodicity of trajectory. So one can, I mean, fit them. These conditions are in the form of a certain of matrix which should not be of the highest, which should have rank smaller than it is the maximal possible rank for the dimension of matrix. And the coefficients of matrix are expansion in coefficients in the Taylor expansion of square root of this underlying polynomial. So, I mean, it is not that easy. Yeah, okay. I mean, it plays, everything plays just, it turns out to be in the plane case, it is equivalent to some, as it was Jacobi's result, equivalent to, as addition theorem to elliptic function. In higher dimensional case, we have hyperelliptic functions of corresponding order. So it is not exactly trivial. It becomes linear on the Jacobian of the corresponding curves, but just to do computations explicitly, it's not easy. However, if you want to get them numerically, it can be easier if you are more because if you have a good computer simulation, you can little bit shift the coefficients and this until you get that they almost that they coincide or almost you get periodic, and for producing nice pictures it could be enough.
Okay.
Yeah.
Thank you. Thank you.
Yeah. Thank you for your question.
Okay, any final questions from anyone? Okay, well, in that case, let's conclude by thanking Milena again for a very interesting talk. Thanks very much.
And thank you for attending my talk and for inviting me once again. Thank you. It was a great pleasure.